Chemical reactions. What influences reactions? Remember, when we're talking about reactions, we're talking about making bonds, breaking bonds. All bonds have to do with electrons. We don't really care so much about the nucleus. We care about the electrons, or at least the electron potential valence shells. Temperature can influence the rate and likelihood of reactions. Temperature is really a representation of how fast atoms are moving. If you have water in a pot on your stove and the heat is not turned on, water's just at room temperature, all the atoms within that liquid mass inside of the pot are bouncing around. But not so fast that they get expelled from the pot, not so fast they turn into steam that much. Some of it does evaporate, some of it does vaporize away, some of them atoms do get lost, but not very fast. When you turn on the stove, you input a bunch of energy, heat energy, and it makes those atoms move around a lot faster. When you have atoms bouncing around a lot more and bumping into each other a lot more, it's more likely that you can make reactions. You can introduce two atoms to one another that maybe are inclined to bond. If you bring the temperature down and slow down how fast those atoms are bumping around, you reduce the likelihood that an atom is going to find something that it wants to bond with. Similarly, if you're in the business of breaking bonds and you have the right extra stuff in your solution, cranking up the temperature can ease the transition into breaking bonds. You've input a bunch of energy into the system. You need energy to break certain bonds. And so when you do that and you introduce the right extra stuff like enzymes and things, you can potentially break a bond. Concentration or pressure also increases the likelihood and rate of reactions. The more densely you pack in atoms, the more likely it is that they're going to find something they want to bond with. The more pressure you put something under, the more densely packed things become, and therefore, the more likely it is something is going to get shoved up against something else it wants to bond with. It's easy to sort of think about these things in too abstract a way. I remember being surprised by the simplicity of this concept, that something has to be right up against something else in order to bond with it, in order to do something with it. It's not like they're going to be spontaneously attracted to one another by fate from other sides of a container. You have to force these two molecules right up next to each other, or these atoms right up next to each other, and only then, if they have the right valence situation going on, there's enough temperature, there's enough pressure, whatever, only then are they going to bond. So by increasing the temperature, you're creating a situation in which atoms are bumping up against each other more. By increasing the pressure or the density or the concentration, but also density. It's basically the same thing as concentration, but by increasing the how tightly packed atoms are with one another, the more likely it is it'll be close to other things, and maybe one of those things is something it wants to bond with. Particle size can influence reactions. Large particles have more stuff, but need more energy to do any kind of work. If you input heat into a system, big molecules are going to require more heat to get bouncing around than little molecules. But big molecules have more stuff on them. And the fact that they're simply bigger means that they're more capable of touching more things. Therefore, they're able to make more bonds with whatever's around. It has a higher likelihood of making bonds because it's just bigger and it's more likely to be touching something around it that it could do something with. Little molecules inherently don't have are not as likely to make the appropriate bonds because they're little and therefore they're touching fewer things, but they're more easily influenced by things like heat. You can crank up the heat and they'll start really bouncing around like crazy. So once you input this extra energy into a system, some of these molecule or particle size differences wash out a little bit more, but they are both still influential. How much surface area something has. If you have a molecule or something that's shaped like this, it has a certain amount of surface area. If you squish that shape down and make it ridgy, now suddenly you have a lot more surface for the same volume. Let's pretend, I don't know, volume is 1. This volume is also 1, but you have a lot more surface to deal with. Reactions, diffusion, osmosis, moving of molecules in and out of your cells, all require to operate across a membrane. They all require a surface. Therefore, surface area is a big factor in what a cell can do and how well it can do it. You're going to find that places in your body that want to absorb things, that want to take in lots of molecules efficiently, have very convoluted surfaces. And they're lined with lots of cells. And even then, each one of those cells has its own convoluted edge to it. This maximizes the surface area so that it's more likely to touch stuff on its membrane. And since the membrane is where stuff happens, it's more likely that it's going to be able to do something with that thing along its membrane more efficiently. Finally, catalysts influence reactions. Catalysts are molecules that lower the activation energy for a reaction to happen. A lot of the chemical reactions that happen in the cell could happen spontaneously, but the likelihood's not great. You either need a lot of time or a lot of energy input into a system for these certain chemical reactions to happen spontaneously. Cells don't have that kind of time. Cells sometimes can't handle that amount of energy. Like if you blast it with enough energy to break up a glucose, a sugar molecule, into two, that's covalently bonded. That's the most secure bond we have. It's going to take a lot of energy to break that. The whole cell might die if you input that much energy. So cells have things called enzymes, which are catalysts, that'll come in and it'll create a situation, usually by changing the shape of something, that ultimately makes it easier or more likely for a chemical reaction to happen. It lowers the amount of energy you need in the system for a reaction to happen. And again, usually it does that by changing something's shape. Catalysts and enzymes do not make reactions happen that would not otherwise happen. They do not create reactions. They find molecules that are inclined to do a certain thing anyway, but it just might need a lot of effort. And then it comes in and reduces the amount of effort you need to do the reaction. It'll only be able to do that trick on things where that is possible in the first place. They cannot force a reaction. I say this over and over and over again because it's a very common misconception. It's easy to forget halfway through the semester that this is the case because we talk about enzymes and catalysts in such a way that it feels like they're coming in and doing things for us, and they're really not. They're coming in and they're tweaking something a little bit so that something else is more likely to happen. There's two major types of chemical reactions that we should think about in terms of energy: endergonic and exergonic. So first of all reactions are considered reversible. It might be really hard, but you can reverse them. You can form bonds, you can break bonds. Reactions that can spontaneously happen, put two molecules next to each other, see what they do, will eventually spontaneously happen. But again, you might need a ton of energy to make that happen. When these reactions happen at an equal rate, when you have forming of bonds and the breaking of bonds, we refer to that as chemical equilibrium. When you have reactions that are happening, whether totally spontaneously or with the help of an enzyme, and in the process of doing that reaction, you give off energy, the products at the end individually have less than the beginning of the reaction. That's referred to as exergonic. Think of it like the big molecule altogether had an energy level, I'm just going to make up numbers, an energy level of 3. You break it in half, each one of the things it ends up with have an amount of energy of 1.5. This guy is less than 3, therefore energy had to be given up. Or sorry, I should say like 1. 1 and 1. You still have some energy that hasn't been turned into those end products. That energy is going to be released into the immediate environment around the reaction happening. It's going to represent itself as heat. That energy, if something else is close to it, can be harvested to do more work. Energy released into a system can be harvested to do more work. You start off with a molecule with X amount of energy. Chemical reaction happens, whether spontaneously or with the help of an enzyme, and you end up with a final product or products, the sum of which is less than what you started with. The difference goes into the immediate environment around the reaction happening. And if you've got a molecule that needs energy to do something that's right up against this reaction happening, it can take that energy and use it to do stuff. The opposite is an endergonic reaction, where it absorbs energy. The products have more energy than the initial reactants. That energy can then be released. You can undergo an exergonic reaction to do work. We oftentimes, but not exclusively, think of endergonic as building molecules and exergonic as breaking molecules. That is not a universal rule, but it applies enough to keep that in your pocket. Some chemical reactions involve exchanging whole atoms within a molecule. The 3 major types of reactions that we're concerned about are anabolic or synthesis reactions, catabolic or decomposition reactions, and exchange reactions. One mnemonic that I use personally to keep these straight, if somebody is taking anabolic steroids, they're using it to build muscle. So anabolic stuff is building, so it's synthesizing, it's adding stuff together. A synthesis reaction, an anabolic reaction, you end up with just a combined product from the sum of its parts. A plus B equals AB. An oxygen and 2 H's is H2O, water. Adenosine diphosphate plus a phosphate equals ATP, adenosine triphosphate. This is the major energy molecule in the cell. A decomposition or catabolic reaction is where you take one molecule and you break it down into its constituent parts. AB becomes A plus B. Synthesis reactions are often endergonic. They require energy, and they require energy to happen, and the end product has more potential energy than the sum of its parts. Catabolic is usually exergonic, but again, not a hard and fast rule. Sodium chloride, salt, when you dissolve it, becomes sodium atoms and chloride atoms. Adenosine triphosphate, that energy molecule, gets broken into adenosine diphosphate and a phosphate. The release of energy from ATP becoming ADP and phosphate drives many chemical reactions in the cell. When we say that ATP is the main energy currency of the cell, what we're saying is that ATP has a boatload of energy in its phosphate bonds. It has 3 phosphates, hence triphosphate. Adenosine, triphosphate, 3 phosphates. When you pop off a phosphate with the help of an enzyme, it releases a boatload of energy into the cell, into the immediate environment around where that ATP is getting broken. If it breaks next to something else that needs energy to do work, that thing can harvest the energy that's released and do its work. It can share that energy. It's a pretty cool trick. But this breaking, this catabolic reaction of ATP is really what we're talking about when we say that ATP has energy, the energy that the cell needs. Exchange reactions are where you swap parts. So AB plus C becomes AC plus B. You just swapped around where the C is. Everything is equivalent. No atoms were removed. No atoms were added. You simply changed around their orientation. This is something that we see a lot in metabolic reactions, where we maybe take something away, but then we put something there, and then we switch them around into a different sort of physical organization in space, and then that makes it easier for another thing to happen. This happens a surprisingly large amount of times. We think about these two the most, right? But this, again, particularly with metabolic stuff, becomes very important. Redox reactions are reactions that involve exchanging just electrons. The first 3 that we were talking about, catabolic, anabolic, exchange, involves swapping whole atoms out of between 2 molecules. Sometimes we're just swapping electrons. Think back to the bonding rules, right? When you're with an ionic bond, you have one atom that really wants another electron to fill its outermost valence shell so that it's nice and stable. Again, not neutral, but stable. And you have another atom that's just got one lonely little electron in its outermost valence shell. It'd rather just get rid of it so it can be nice and stable. Again, not neutral, but stable. And so an electron will pop on over and get moved. When electrons move around, this allows for a whole new extra range of bonds and attractions to happen. You can do this within molecules and within chemical reactions. You might swap different atoms around within the system, but then they're next to different things. And now that they're next to different things, they might be able to do different tricks to make their outermost valence shells happy. When you reduce a molecule or reduce an atom, it takes electrons. If you oxidize something, you give away electrons. Again, this oxidation part has to do with early stages of chemistry and what molecules they were using to do these experiments. It does not always involve oxygen. It does not have to have any oxygen in it whatsoever. Giving away electrons is oxidation. The lose electrons is oxidation, gains electrons reduction. Hopefully you remember that from Intro to Bio or an old chemistry class. Most metabolic reactions involve redox reactions. So we have a lot of exchangey stuff going on, and we also have a lot of redox reactions. In this example with table salt, sodium chloride, this is an example of a redox reaction. Chlorine got an electron. It received an electron. This was reduced. Sodium gave away an electron, therefore it was oxidized. Just to stress, once again, there's no oxygen involved in this whatsoever. Sodium gave away an electron, therefore it's oxidized. Chlorine gained an electron, therefore it's reduced. All of these different bonding types, all of these different chemical reaction types can be happening simultaneously as one another within the same subset, within the same little handful of molecules. You're going to be seeing these terms be thrown around when we're talking about different reactions happening, again, especially with metabolic stuff. You've got a reduction, you've got an oxidation, you've got some exchange reactions happening. You might have an exchange reaction to facilitate a redox reaction. Because so many of these principles are going to crowd into one another an awful lot or build up upon one another an awful lot, it's very important that you keep these concepts straight.